I'd like to introduce, welcome to the speakers, Julia Neumann, Daniel Hirschroy. That's your last name is so complicated for me. Daniel, I'm sorry for that, and Maximilian Gruber. I also want to ask you, to the participants, to write your questions directly in the chat as they come to you, and we will answer to them at the end of the talk. That's from my side. Probably this is also the time. Let me extend it a little bit. That you are welcome to participate with more talks in either of the three formats we have thought about that are available. Short talks like this, non-expert or expert talks, very in-depth presentations, but also on the format of hands-on short training workshops. So if you're interested, please contact me. Another point that is general information that I have to share with you is that for to avoid some legal issues that we found in the way about the CABUREC sharing information from you into TC6 because we are kind of a third party. So we ask you to register directly in IMEKO TC6 to continue participating in this serial talks, serial webinars. So the floor is yours, Julia, Daniel, and Maximilian.
Thank you for the introduction and thank you for having us here today. I'm going to share my screen and the slides hopefully in a minute. So we are going to talk about semantics today. The talk is divided into three parts. The first part that I'm going to present is about the basics of semantics and knowledge representation. The second part is going to be about examples and metrology for semantics. And the third part is going to be about how to create knowledge sources that are based on semantics. So I'm going to hop into the topic right away. So what is semantics actually? It is the meaning of science. It comes from a Greek word that actually means to signify, to mean. And yeah, here in this talk, we are primarily talking about linguistic science, so the linguistic knowledge of semantics. It could be also potentially a programming language. It also carries semantics and other logics outside of the box. But I'm going to talk about the linguistics aspects of it. You see in the slide some pretty pictures, which I'm going to explain a little bit further here. So what is semantics? We have an object that could be, for example, an apple. And we, as a community, have a concept of it, how it looks like, whether it's red, whether it's green, whether it's fresh, whether it's sparkling. So we have agreed upon what is actually an apple, what do we think of it. And then we have a third entity here in this picture, which is the actual written sign, apple written out. And those three components actually contribute to it that we create meaning to something. And if we only have just the object, that's actually just only one part of the meaning, but it's not the actual whole complex of the meanings that we talk about when we think about semantics. So semantics can be actually the key for interoperable data, but it will not solve all of the problems by itself. And I think by the end of the presentation, we will all know what we mean by that. So I want to go to the next slide, but how do I do it? Okay, sorry. This slide here is to show you what does semantic actually help with. You see a lot of hammers here. This was just a simple Google search that I did years ago. And you can see that just the word hammer can have a lot of meanings. It could be a brand. It could be just a physical hammer to repair things of handyman, but it could be also just a plastic hammer, like you can see, so really different meanings. And on the right side, you see like a sign, a crushed person. And with this, I want to show actually that semantics can have different depths of expression. So we all know that the sign on the right means danger in some way because it's red color and you visibly see a person being crushed, but it's not always clear what the sign is called, for example, but you still have some point of meaning here. So there are further examples where you actually might require semantics, for example, for clustering of documents or classification of documents, annotating documents, tagging them, but also more like complex tasks for information seeking and information retrieval, such as archiving too, but also database development and interoperability if we go further into the aspects of machine to machine and human machine communication. So the conclusion for this would be that we have this process of digital transformation going on in a very fast pace. And we have more and more tools and concepts and metrology that also connect to quality infrastructure, especially. And this fast pace of innovation actually requires that we understand each other, and it will be more and more crucial. We have seen that signs are one aspect of semantics, but the guy you see here is Tim Berners-Lee, who founded the World Wide Web and Semantic Web, and he actually established that just having a sign isn't just one part of giving meaning to something. We also need to have relations between our concepts that we have in mind as a community, and through the relation to what is something in comparison to something else, we also create a meaning. So we need to figure out how to create such a structure, or a web, how he called it. So there are blocks of the semantic web that define what you actually, or what kind of components you need to have in order to create relations. One is formal logic. That would be something like roots and data, but also reasoning about the content that we are filling with in the database, because we want the machine actually later, not only the humans, but also the machine to understand it. So we need to be able to express complex properties and to remain decidable in that. So the second part of the block is integration with the existing standards. So we actually need standards to be able to have a common ground to understand each other. That also applies to that we need to use tools that are accepted by a major community, but also that we decide on annotations, such, for example, XML, or specially created schemes for semantics like RDF. We are going to talk a little bit about that later. Or and the third block would be the available collections of information. So we actually need information, first of all, to be able to do something to relate to each other. Without that, we can't do that. So we need actually a domain, experts, a community that have a specific knowledge and concepts that we can relate to each other. I'm going to go quickly over this slide now. This is a semantic web tool stack. So like I said in the previous slide, like just having a content isn't enough. We actually need like some sort of architecture that or infrastructure that works together and combines the content part with the technological part, so we actually can create meaning that is machine readable in the end. So one part of it would be, for example, that we actually have a user interface with applications, and which is filled with like logics, data schemes, but also with such things like databases or thesaurus and ontologies that have the content, and furthermore that we can actually query those databases, like for example with a Sparkle query language. And we have many different other layers, which I'm not going into detail here, but the main takeaway is that all the data that we have and the metadata that we have requires a unique ID, references for linking of data to each other. And we have an example here in the corner of a link as such. So the basis of relating information in a machine understandable way is the resource description framework, short RDF. We have a quite simple structure, which is consisting of a subject, predicate, and object. Those of you who know how to program will relate to it and know something about it already. So we have, for example, a measuring device, and we could say that the measuring device is doing something with length. That is our subject. And this length might be something that is 25 millimeters long. And we can actually divide this information into a predicate by saying, okay, we have this object 25 or millimeters, and that's our value, and that is our property to it. And we can describe just this measurement device with those three entities. And actually, that's the main idea of the resource description framework, that you can depict meaning just by having those three relations to each other. So not only you have to be able to like decide what subject, predicate, or object is, but the trick is also to fill the content correctly. And therefore, there are also standards like the Simple Knowledge Organization System, like SCOS, or Web Ontology Language, OWL, that give a formalized way on how to fill the content into those tuples. One of those, knowledge representation forms is ontologies, which I want to go a little bit deeper here, is ontologies traditionally refer to outcomes from a harmonization process and philosophy grouping, that all beings, things, and basic structures of our reality are in one unambiguous system of knowledge. That's like the Wikipedia definition, but basically what we have like in our real practice examples is that it is a formal representation system of knowledge within a specific domain using that schemes that I showed in the previous slides. And you will also see this like triple structure from before here too, depicted by, for example, that ontologies are using such things like entities, similar to subjects, like that something is an artifact, for example, but it also uses other parts like expression forms. So we can say that a measurement device has subclasses. For example, we have something that measures weight, we have something that measures speed, so we can divide it into subclasses as such. And then we can go deeper into properties, something like, okay, it has a range or something like that, or it has a specific color, for example. So we can actually build a pretty clear structure with it. The basic idea of ontologies and of many knowledge representation forms besides ontologies is that we follow an open world assumption. What does that mean? It means that we all have our voices, and the semantic web itself is open to all of the voices, means that this something is missing in an ontology or a thesaurus or a taxonomy, whatever it is, this is not wrong if something is missing. It is simply not yet in the database. It's simply not there yet, but it is not wrong. So we have a nice example here on the right side. If we assume that Alice, who knows Bob, both have each a dog and a cat, we still don't know from this representation that we have on the side whether Alice has an own cat or if how many cats Bob actually has. So we cannot actually tell everything from this depiction yet, but we could at any time add it yet. So that doesn't make it wrong yet if it's still missing. So I'm coming to the last slide of the first part. What are the pros and cons of the semantic web? So we have this big pro actually that we can solve extremely difficult problems of information interoperability with semantics because we can be very flexible in building relations and relation types. And we can break up data silos quite easily with that now. And we have the potential to enable machines to better interpret data. For example, if we use the concept of fair data, we can now ensure that we find data better, but also make it better interoperable by communication with humans and machines. The cons of it are actually that it is rather difficult to grasp the structure of the relation types and the schemes that we have. So you need some training to actually be able to apply it. So that's definitely a con. And there are quite a lot of policies that could prevent access to linked data. So speaking of, for example, vocabulary or controlled vocabulary such as dictionaries or thesauri, often they are like belonging to a company or an institution that has a license behind it, so you just cannot simply copy and paste it to your own project, which is something to consider as a con here. And the quality of the data depends, of course, on how the technology is used. You can have good data, but if the interface isn't working for the end user, like you're not going to have any benefit out of it. So you actually need a programmer who knows that too, in that sense. And of course, we have such things as ambiguities. That things can have many double meanings, for example, and to split those double meanings and to actually correctly sort them into a database is fairly challenging at times. So that would be for my part.
Great.
And I would take over to the next person.
Thank you very much, Julia. I will just try to take over the screen now. So as Julia said, one of the building blocks of the semantic web is the availability of existing knowledge graphs and knowledge resources for specific domains. And in the second part of this talk, we want to give some examples of existing semantic knowledge semantic knowledge sources, which have a more or less direct connection to metrology applications. So, yeah, that works, good. So Julia already said that there are some more fundamental namespaces in the semantic web, and these are the RDF namespace and the RDFS namespace, and these are used for basic data modeling. So to specify subclass relations, subproperties, lists, domain, range, type assertions, and so on. And I've taken here a very naive choice, maybe, but to give a more metrologically flavored example, at least, let's assume we have a property that's called traceable to something. And we can then say, okay, this traceable to property is of a type of a transitive property. And this property would be a subclass of a more general property in the RDF space. And you already see here a concept from the OWL namespace, and that is used to express more advanced ontological properties and attributes of concepts. So what that allows us to do is that we can enable advanced reasoning through this vocabulary. So in this case here, we have the property traceable to, and we say that it's a transitive property. And that would mean that if we have A is traceable to B and B is traceable to C, then we could also make a machine do the reasoning and say that A is also traceable to C. That's the idea of it. It's of course a very simplified version, and I'm not saying that this should be how it's implemented, but just to give you an example here. And then we also have, which Julia already also mentioned, the simple knowledge organization scheme, which is more intended to provide additional information about your, or more human readable information about your vocabulary that you might plan to develop. But it also allows us to, but it also allows us to define related concepts or a closer match or a narrower match. So to just give you an example of what also could be done, I just forgot that to say that. We could say that traceable to is the inverse of calibrated by. That's up to debate if that's really the case. But this is one way to expand knowledge and to let the machine in the end do reasoning by including properties that have more meaning in the OWL namespace. And then we could use SCOS to say, okay, traceable to is related to the metrology domain, or calibrated by has a preferred label that you could use if you want to display that in a user interface or a human readable user interface. Another vocabulary or ontology that's already out there is the SI reference point. And that's an ontology to capture the knowledge of the SI brochure. It's already online, it's public, it's reusable, and it's currently in the beta stage, but in a quite late and stable beta stage, I would say. And you can access that under this domain, and it allows you to define or provide PIDs for various units that are in line with the SI brochure. And if we now might want to obtain some knowledge out of this knowledge graph, you could use the Sparkle querying language. And I want to go through this example in a bit more detail to show you how you can access and how to traverse a knowledge graph. So what we do here is we ask for, there is a placeholder. So question mark prefix is a placeholder or variable. And we ask for all triples that match this placeholder. So all placeholders that are a SI prefix, that's what we want. And then we ask for additional attributes of this placeholder. So we ask for a label, exponent, and a symbol. And we also do some sorting and filtering, but that's not too important for this application here. And in the end, the Sparkle query returns these extracted property values that we've defined before. And if we then list all the results that match our query, we obtain in this case, a list of the prefixes that are mentioned in the SI brochure, and also their exponent value and their label. So what you see here is that this more or less recreates the essence of what is the SI prefix table in the SI brochure. And I think, Daniel, the next example will be then explained by you. So
Thank you, Max. Exactly. And I tried to take over the screen again. Now I can control it. No, okay, perfect. Yeah. So also hello from my side. Thanks, Julia and Max, for the introduction. So I like to continue this example from the SI reference point. Now going to an example of an ontology you can use to exchange actual measurement data. So the SI reference point was defining the concepts of the SI brochure, of the definition of the SI. Now we look at an ontology in some sense layering upon that and allowing you also to transport actual measurement data. So here you see the SIS ontology. SIS is for SI semantics. It's an ontology implementation of the DSI data model that's used, for example, in digital calibration certificates. And this model defines, in addition to the SI reference point, a concept called quantity value. And if you know the international vocabulary of metrology and the guide to the expression of uncertainty, then you will find this term at many places, standing for concept, a data structure, providing the means to exchange actual measurement data, including numeric values, units, but also all kinds of measurement uncertainty. So here you see an example. It's also based on the structure of RDF, of knowledge graphs with subject, predicate, objects. You can create a more technical data structure, like a database model almost, of measurement data using such ontologies and semantics. So the quantity value on the one hand has a property, object property pointing to some measurement uncertainty information. I won't go into detail how this measurement uncertainty looks like, but you can think of that this model has probably many subclasses like expanded measurement uncertainty, standard measurement uncertainty, and so on. And on the other hand, we can link this information about quantity to knowledge graphs describing our systems of units and quantities. Like here's the example drawn up that you can say the quantity value represents a quantity kind defined, for example, in the SI reference point. And you can also link the used measurement unit based on a notation from the SI reference point. But as this ontology is also used in many different areas, like in research data, it also allows to link other kinds of ontologies and knowledge graphs. So also very common used in research domains is the so-called QDT ontology. It stands for quantities, units, dimensions, and types. And in the same way, you can also link in this knowledge graph the quantity kind definitions and units in the system. And that's also a great example of the previous mentioned open world assumption. So today we have many representation systems for similar things. So it means also in future in our semantics, in our knowledge graphs, we can express this multitude of existing systems by allowing links to different systems. And also I like to give credit and acknowledgement to my colleagues Moritz Jordan and Giacomo Lanza, who are really doing excellent work to develop this SIS ontology and to advance it, including such links. If we go one layer upon this, then the quantity value has different implementations in this ontology. This is called subclasses, a concept or properties mentioned before. So while quantity value is the generic concept in this ontology knowledge graph, we have then specific subclasses like real, SIS real, that's in line with Vim and Guide to Expression of Uncertainty. A Scala real quantity value, providing values, units, but also additional information like timestamps of measurement or information about potential significant digits. And there are more concepts like values of fundamental constants, SES constant, or you even have vectors, respectively, lists of data that may share a common unit and quantity kind, which you can also express through these knowledge graphs in RDF. Okay, another example. So we go again one level up. So we had ontologies for unit definitions, then we had an ontology for measurement data. Now we have a much more sophisticated ontology example from the Surpass 2 project for digital product passports under the sustainable product regulation of the European Union. So this ontology defines many sub-ontologies or modular ontologies, like there's an ontology specifically for product properties and information about this digital product passport. There's an ontology defining properties for actors, which could be manufacturers or conformity assessment bodies. As it is about sustainable products, we also speak about information about substances of concern. So here we also have information about certain materials we also use in metrology. And there's also information about compliance, in this case, in particular, information that you can find today, for example, in a declaration of conformity coming with products like measurement instruments. And all these individual modules, they can be operated on their own, but as these ontologies can also be imported in a overarching ontology. Here it's called core ontology. So this means if you have defined semantic in one ontology, you can reuse that to create new ontologies based on that, or to put together the ontologies you need. In this example, also the SI reference point is used to address units of measurement and to foster also connection between the knowledge graphs of the ontology modules. A so-called connector ontology is defined here, which is a very powerful tool. So it's an ontology just containing properties that connect information from these ontologies. Like you can say digital product passport DPP has a certain manufacturer and actor, or the product passport is associated to a certain declaration of conformity and so on. And now I switch again. Here's now an example about more comprehensive work of German calibration service, establishing a controlled vocabulary for terms and terminology used in calibration data, like digital calibration certificates. They are working to set up a thesaurus to provide various information about terms used in this calibration certificates. These terms are called ref type, or ref type is the root concept, which is vocabulary identifying the meaning of measurement data in particular in calibration certificates, but not only. And here you see that terminology is not simply a linear list, but different levels of meaning can be associated. So here, ref type is very generic. On the next level, you distinguish between different metrological areas like mass and force, but there's also a common category of ref types like basic, where terms are listed that hold true and can be used by all different metrological areas. And then each of these subcategories like basic and mass, they have again individual collections of terms that have been created and agreed by representatives of laboratories working in the DKD German calibration service. And the relation between the concepts is that the more general terms are called broader terms and more specific terms are called narrow terms. And now the title of the presentation says semantics, it's not rocket science, because here in the end, the technical implementation is not a difficult thing. The challenging thing is that the community, the people from the laboratories come together and agree on the content of this database for ref types. And what they do, they have defined a template of information they want to provide for each of the terms in this thesaurus. And they sit together in online meetings and fill in these templates. And in the end, only some editor of the thesaurus is filling that into a machine actionable database. Just to let you know very briefly, so for each of the terms here, they collect the broader term. They say what's the label, like measured value that's displayed in the database. They provide the definitions of the term in different languages. If the term has been defined by some guidelines that already exist, standards and so on, they can refer to that, like a literature reference. There could be examples and scope definitions in that definition. And you can also put in references and relations to other concepts. And all that is mapped to SCOS properties like labels and definitions, which is allowing a very flexible setup of such a thesaurus and including links to also other systems like Electropedia in the future, or NCSLI also has a measurement taxonomy that could be linked in here as well. And as in the SI reference point example here, also the system provides a Sparkle query endpoint. One competency question we are looking here at is to this thesaurus, give us all relations that express the taxonomy of all terms in this thesaurus. So it looks technically, but again, in a query defined by such subject, predicate, object relations, you can quite easily extract a long list of all the broader and narrow terms included in this thesaurus. So narrow and broader are variables defining these two terms. Like here, you can see an example on the right side. The basic is a broader term, measured value is a narrow term. And with this Spark query, you can extract lists of all these pairs of broader and narrow terms in the thesaurus. And for each of the term, you can also extract the more human readable labels like basic and measured value. But of course, you can also define other Spark queries depending on the information you need from that system. And I think with that, Max, it's Max's turn again. Thank you.
I just want to mention two further examples of knowledge resources or semantic knowledge resources that are already out there. And one is the semantic sensor network ontology. So in case you have use cases where you want to describe the interaction of sensors in a more industrial context, so to speak, but at least that's the intention of it. We can probably use it for other things as well. There is a sensor, or a semantic knowledge representation for that. So if you want to represent the sensor with where is the sensor hosted, what kind of variable or quantity is the sensor observing, there is something out there. And if you look into the details of the, or if you search for semantic sensor network ontology, you have a very good documentation that you can find there. Another ontology that's quite important to metrological applications is probably the provenance ontology, which is used to describe the relations between, or to provide provenance by providing the relations between agents, entities, and activities. So an agent could be something like a person, an organization, maybe an NMI in the case of metrological applications. It could also be a software agent. And these agents can then be can be part of an activity, and activities could be something like an evaluation or an assessment of something, maybe a production of something, or a measurement or a calibration step. And these activities then lead to entities that are more or less the outcome or the input to an activity. So an entity could be a collection of things, a bundle, a plan, some document, maybe a certificate. So it's a highly generic, or it provides highly generic vocabulary that can be specialized for certain use cases. And this leads us a bit to the question, how do we actually create knowledge sources? I think Daniel already said that the most important thing is not the technical implementation of the ontology. But the first thing that you want to do is in ontology engineering is to make sure that your domain has a shared and non-digital understanding of its knowledge. So you need to harmonize first before going the step and having a digital semantic knowledge representation. And what you also should do in advance before starting to do anything is specify what kind of questions you want to be able to answer with your ontology. Because you can model quite a lot of things on the knowledge modeling side of things. But the question is whether you need those. Because with additional knowledge detail and modeling detail, there's also additional complexity. And maybe that's not needed for your use case. So be clear about what you want from your ontology and knowledge base. And to break that down into a bit more of a practical application, I want to introduce you to some highly toy example-ish pizza provenance ontology. So the first thing that we want to do is to define some core concepts. And in our case, this is probably a restaurant, a customer, and a pizza. So because we want to model pizza provenance. Then we want to align our knowledge graph with other knowledge graph, because in the same sense as the World Wide Web works by linking multiple resources, also the semantic web works only by linking different knowledge graphs. And then we see, okay, maybe a customer is probably an agent in the provenance ontology. A restaurant is also an agent. The pizza is an entity because it gets produced. It's a thing. But if we then continue thinking about it, it's probably good to have additional concepts. So we introduce also the concept of placing an order, the preparation of a meal, of a dish, and also a cook. And then we might also think even further about it and see, okay, these can also be aligned to the provenance ontology. And then our pizza is probably, what we mean by pizza in this context here is probably the item on the menu list. So we might have food items, drink items, and these are subclass relations. So these are the taxonomic relations in our ontology here. Then come the non-taxonomic relations, the additional relations, which make the ontology actually an ontology. So we might say, okay, a customer places an order and this order is then made at the restaurant. And by that, we also have a connection, a multi-step connection between the customer and the restaurant. We then say, okay, the order probably contains a few menu items. And then the order invokes a preparation of the meals that prepares the dish. And the preparation is done by a cook. And then the dish can be delivered to a customer. And that's a bit how you see how a network of knowledge forms. So that's why we call it knowledge graph. And what we have here now could then be also annotated with additional metadata and descriptions using the SCOS framework. And that makes up our core terminology. So these are the basic things that we need. And only then, when we have that, then we can start to serialize that into a digital format. So all the major work starts on the non-digital side, on the harmonization side. And once we have then serialized it into RDF, we can populate it with individuals if needed. So with specific instances of the core concepts that we had. And we might also want to introduce quality checks, like answering the competency questions in an automated way to see if our expectations match our actual implementation. We could validate the graph for inconsistencies. We could do additional checks like highly systematic logical error checking. And then if you really go far beyond the scope of this presentation, you could also add more closed world constraints into your knowledge graph. Not into the knowledge graph, but by using shackle constraints. So that was just to give you a very quick impression of what is ontology engineering. Daniel, I think we did not speak about who should conclude the presentation. I could just do it if you want. Yeah.
Yes.
All right. So machine action only semantics are typically based on the semantic web technology. That's the best that we know so far. As Daniel and I think Julia even also said that it requires harmonization based on human interaction first, and only then comes the digital part. And there are already quite a lot of knowledge graphs out there that are suitable for metrological applications. So with that said, we also would like to make you aware of certain references. So if you want to have a bit of further reading, there's the original article on the semantic web by Berners-Lee. And there is some ontology 101 by the Protégé project. There's also an ontology engineering book, multiple W3C ontologies that we also presented here in the talk. The SI reference point is listed here, the SIS ontology, and the Thesaurus web UI. And if you have read all these or you're ready to do very semantic work, there are also quite a few tools out there that help you with that. So there's the Protégé front end to develop and inspect ontologies. The Thematress is also a web UI to display and develop knowledge graphs and vocabularies. There is the EU Workbench. There are two main Python packages. There are even more, but two very important Python packages, the RDF-lib and already2, to deal with knowledge graphs. And then there's also Scosmos and WebWall for visualization. Yeah, and the obvious IMEKO, I think, World Congress paper, Daniel, I'm not sure. Was it?
It was TC6 conference.
Ah, the TC6 conference, sorry. I mixed that up. Yeah, but if you want to have a read through that, I think it also summarizes a lot of the essentials on semantic knowledge and metrology. So I hope this was something interesting to you, and it contains some new bits that you haven't seen so far, and we are looking forward to your questions.
Thank you very much to the speakers. Thank you for sharing your knowledge. Excellent presentation. Please, if you have any question, send it by the chat. I already have one question, very basic, as I'm new to this technology of Sparkle, and I'm wondering if the question from my side is if you can share with us if what is required to install this kind of tools, or if it's an online tool or environment, I don't know.
So usually it's provided as a web service, and I would probably look for packages that provide this functionality within your preferred programming language of choice.
Okay, thank you.
I think at least Python and Java should have something ready to be used in the package database.
Mm-hmm. Thank you.
Henrika, I think I saw your hand raised up, but maybe we already answered your question.
No, if it's okay to ask the question out loud, I would prefer to do that. So, yeah, I have a question about how to use these ontologies in like a practical application, for example, in the DCC. So if I use the DSI package to for my units in the XML, is that already enough, let's say, or do I have to link it to the ontology in a different way to make sure that the units, for example, are machine actionable?
That's maybe a question I can answer. So in the XML implementation of DSI, we implement a service to map to DSI reference point definitions. But if you use the ontology representation and in future also the ontology representation for digital calibration certificates, when you create a certificate, you can put in the link to the respective resource like SI reference point.
Okay. And then for the ref types, for example, just by having the link to the ref type database, which should be part of the XML already, then that's also linking it in a way that's already machine actionable, right? Or should
In this
be
case, the
something
link
different
to
there?
this ref type thesaurus is already included explicitly in the XML format by providing you information about the URL of the namespace, like basic or length. And then you can actually go through an API if you want to have a machine actionable access, go through an API and get the ref type definition for your area, like basic, or you go to the website and look for basic and look for your term.
Okay, thank you.
No more questions, please. If no more questions, thank you very much for your time, for sharing your experience with us. I don't know what else to say. Let's say we can join next talk, and I invite you to register under TC6, IMEKO TC6 again. While in the meantime that we review with Kaburek if they can share your information to this third party of IMEKO. I appreciate your time. Thank you very much.